Today we'll be presenting an article titled Counting on Quantitative Reasoning for Algebra. This article was written by Lori Birch, Eric Telema, and Andrew Gatza, and was published in the 114th volume of the Mathematics Teacher Learning and Teaching Pre-K through 12 journal in 2021. This article explores how algebra teachers can develop students' understanding of algebraic identities and expressions using combinatorial and quantitative reasoning. The authors propose a shift from traditional algebraic approaches that focus on rote memorization of identities toward methods that build conceptual understanding through problem-based learning, particularly with combinatorial examples. This approach aims to improve students' foundational reasoning skills, which can help reduce common algebraic errors when, for example, expanding expressions. Underlying this approach is an emphasis on the first strand of algebra, described by Caput in What is Algebra? What is Algebraic Thinking? To be the study of structures and relations, especially as used in quantitative reasoning. The authors of this article argue that Caput's support for quantitative reasoning skills is seldom seen from math educators today. Instead, instruction has a focus on algebraic symbol manipulation. Most textbooks lack any focus on the abstract reasoning skills students can build from problems involving expanding expressions and instead solely teach students the distributive property and FOIL method. I believe many students can attest to this in their own experience with algebra. Personally, I never remember doing any problems with expanding expressions in algebra that actually required reasoning. In fact, I remember being very confused about the binomial expansion during my time in a combinatorics course here at UIUC, and it was only when I saw the combinatorial approach to it that I actually understood the meaning behind the expansion. So, a concept that I learned years ago and was required to use in subsequent math courses throughout college only finally made sense to me after the combinatorial reasoning behind it was explained, and I don't believe I'm the only one who had this experience. So, while the goal of expanding expressions in algebra classrooms is currently to simplify to the final polynomial, the authors want the goal to instead be for students to understand the structure behind the expressions they are given, why this structure leads to a specific expansion, and what the structure of the expansion itself means, which can be done using combinatorics problems. So, instead of just learning to expand binomials by a memorized process, students should develop a foundation in quantitative reasoning in order to understand why these identities work. Specifically, the authors of this article claim that errors such as believing that the quantity x plus y squared is equal to x squared plus y squared are being routinely made by students, and that these errors can be reduced if students understand these multiplicative structures more deeply, especially using mathematical models. These remarks are reminiscent of those made in Beyond Rise Over Run, A Learning Trajectory for Slope, where the author, Peck, argues on page 434 that the concept of slope needs to be taught in a meaningful and not rule-based way. Otherwise, students were shown to be quick to miss the actual meanings of slope within various problems. In comparison, the authors of this article would argue that if we teach the algebraic concept of multiplying and exponentiating expressions with variables in a rule-based way, solely relying on FOIL and the distributive property to help students complete problems, then students will miss the actual meanings of the variables and expressions they are working with. Thus, the authors call for a switch to introducing approaches to algebra problems that require quantitative reasoning from students, even if the rule-based method is quicker or easier to teach. In particular, combinatorial approaches to algebraic problems are recommended by the authors, one of whom has their main research focus in finding how to integrate combinatorics into high school math. Combinatorics, though a college-level math course, is based on counting different arrangements of objects and thus relies heavily on making variables to represent the objects one is counting and then creating expressions to correctly count them in a certain context. The importance of variables and expressions in combinatorics is something that is absolutely necessary in the teaching of algebra, and thus, the authors propose that it makes sense to shift the algebra curriculum to include combinatorial reasoning. While this shift does require work, going the extra mile to create these connections for students is worth the time, an idea we will revisit at the end of the presentation. To give an example of a problem within the context of this article, we look at the expression the quantity x plus y cubed. We want students to get the answer x cubed plus x squared y plus y squared x plus y cubed. And more importantly, we don't want them to get x cubed plus y cubed. But what if we could frame the question in a more meaningful way? Here, we present a problem that leads students to solving the quantity x plus y cubed by actually making them build the expression themselves as a representation for a counting problem. This problem is similar to that of the card problem presented in the article. The problem is as such. Suppose Henry has the 2, 3, and king of hearts, Darcy has the 2, 3, and king of diamonds, and Sally has the 2, 3, and king of spades. If one card is taken from each person, how many different 3-card hands are possible? This question turns simplifying the quantity x plus y cubed into a problem that requires quantitative reasoning skills. To solve it, students start by creating mathematical models. For example, the students observed in the article that worked on this question began by drawing figure trees as shown in Figure 3, where they decomposed the problem into possibilities for the first, second, and third card pick. They were then encouraged to adjust their model to a graphical representation, where separate graphs for each possible choice of a hearts card show the possible ways to pick the 2 other cards. Combining these 3 graphs seen in Figure 4, students were then able to transition to a 3-dimensional model, as seen in Figure 7. With the help of computer software, the students were able to see the different possibilities for 3-card hands modeled as an object in 3D space. The typical x-axis represents cards from the diamond suit, the y-axis represents cards from the spade suit, and the z-axis represents cards from the heart suit. The units are king, 2, and 3, representing the different types of cards that could be taken from each suit. Thus, the red region represents the case in which a king is chosen from each suit, which can be seen to only represent one single possibility out of all the 3-card hands. This model connects the students back to the expansion of the quantity x plus y cubed. Students can think of the number of cards from each suit as 1 king and 2 non-face cards instead of just 3 cards. Since each of the 3 people have 1 king and 2 non-face cards, the total number of ways to pick 1 card from each person is the quantity 1 plus 2 cubed. It is now clear that the quantity 1 plus 2 cubed does not equal 1 cubed plus 2 cubed. This is because 1 cubed would represent the case in which only kings are picked, as you only have one option for a king to choose from each person. So 1 times 1 times 1 is 1 cubed. To compare, 2 cubed would represent the cases in which only no kings are picked, as you only have 2 options for a non-king to choose from each person. So 2 times 2 times 2 is 2 cubed. However, this would represent solely the cases where all 3 kings are picked, or none of the kings are picked, which excludes the cases represented by 6 other regions on the model. These are the cases in which a mix of kings and non-kings are picked, and represent the middle terms in the expansion of the quantity 1 plus 2 cubed. Students can then recognize that to generalize this situation, they can represent the number of face cards each person has as x, and the number of non-face cards each person has as y, thus making the total number of 3-hand cards equal to the quantity x plus y cubed. Through this activity, students are able to bring their own tangible meaning to the expression quantity x plus y cubed, and understand deeply without using the distributive rule why that quantity does not equal x cubed plus y cubed. The card problem clearly shows students that expressions are powerful tools for exploring, reasoning about, and representing situations, and that variables have many different meanings depending on context and purpose. 2 of the essential understandings for the big ideas of expressions and variables in this course. The problem helps students to see the meaning of the variables x and y in a certain context, which is something rarely done when learning how to multiply binomial terms. Usually, students immediately learn FOIL. Additionally, by starting with the 3-card problem, which brings them to the quantity 1 plus 2 cubed, and then eases the transition to the connection to the quantity x plus y cubed, students can understand how they can use binomials to represent situations in which they are counting possible cases in a certain context. This process also emphasizes the importance of models in mathematics, as students use three different ones for this problem alone. In Chapter 3 of Beyond Formulas in Mathematics and Teaching, the author Daniel Chazin shows how using multiple representations for problems involving multiplying quantities with variables worked better with students compared to solely ingraining the distributive rule in students' minds. Thus, although it may feel easier to simply teach students how to quickly use the distributive rule, it is actually more beneficial to give students representations of what they are actually multiplying. Otherwise, algebra can feel like busy work with no meaning. Additionally, in the case of Ed Taylor from the book Improving Instruction in Algebra by Smith, Silver, and Stein, the combination of drawn models and a mindful usage of variables carry the students towards being able to algebraically express a pattern's growth. Clearly, it is important for teachers to guide students to create algebraic representations on their own using modeling, in order for them to have a deep understanding of what they are actually doing and what the usage of algebra can look like. This article is framed as a practical guide for teachers to improve their algebra instruction by integrating quantitative reasoning into their curricula. It addresses common student challenges in algebra, such as misconceptions about the binomial expansion, making the article especially relevant for teachers who see these errors commonly occurring in their classrooms. To support their ideas, the authors use evidence in the form of classroom examples. They share videos and descriptions of student interactions when working on the card problem in order to show how reasoning-based approaches can impact a student's understanding of the concepts at hand. They also share videos involving algebra teachers and their discussions on binomial expansion problems. These teachers tended to discuss strategies for expanding a binomial, such as the rational root theorem, factor theorems, or using graphing calculator technologies, all of which do not highlight the structure of the algebraic expression itself. Moreover, the teachers do not focus on the relationships between the coefficients of polynomials and constant terms in the expansion. By showing evidence of teacher discussions regarding this topic, the authors support their case that combinatorial reasoning deserves its place in the classroom to support building quantitative reasoning. The authors use this evidence to argue that this shift will not only help students to understand algebra more deeply, but will help teachers to truly understand what they are teaching. The article references various educational research papers, one choice being James Cappett's What is Algebra? What is Algebraic Reasoning, which was used to support the importance of quantitative reasoning. The authors also reference algebra textbooks, particularly the lack of efforts in them to help students generalize mathematical reasoning skills. The article also cites the Common Core standards for mathematics, specifically the standard for students to reason abstractly and quantitatively. These sources combined add credibility and offer teachers a solid theoretical foundation. The authors conclude that focusing on reasoning rather than rote memorization can create a more meaningful understanding of algebraic structures, and that teachers should shift towards reasoning-based teaching, which can include incorporating combinatorial ideas, such as done in the card problem. The article makes itself useful to teachers by providing actionable strategies to change their curricula and lead students towards a deeper understanding of algebra. Finally, the authors share a quote from a student, Brooke, who reflects after engaging in the card problem approach. Brooke says, quote, "It's so worth it. I know how easy it is for teachers to say, I don't have time, it's not worth it. I'm just going to do it the way I've always done. But it is worth the time." End quote. Brooke's words develop a necessary sense of urgency for algebra teachers, an urgency to go past simply teaching students concepts in a way they can regurgitate on a test. Instead, teachers are tasked with equipping students to reason through problems, to grasp the structures that underpin algebra, and to carry those skills as they venture into more advanced mathematics. Caput points out that the strands of algebra are not just present in the algebra typically taken in grade school, but are vital to more advanced math, including courses such as real analysis and abstract algebra. In conclusion, while a shift in teaching can be challenging, it is a transformative investment, one that ensures that our students don't merely do math, but are instead empowered to think critically and understand mathematics at its core. Thank you.